We're going to be looking at resonance. And when we have pi bonds and charge, or pi bonds and a free radical, what we often will find is that there's more than one valid Lewis dot structure. Notice that word valid is italicized. And the reason that it is italicized is for it to be considered a resonance structure, it has to be a valid Lewis dot structure. That means you have an octet and you're writing formal charge on the atom that would have formal charge. An important concept of resonance is that you are not changing the location of the atoms. What that means is that, like down here in this structure, it's not like you can move the oxygen to between the carbon and the carbon. You have to keep them arranged with the same basic sigma structure. What actually happens is the charge and the pi bonds can move around, not the sigma structure. Now, resonance structure is used as a tool because it helps us figure out why reactions occur or why molecules behave as they do. The real structure is explained with molecular orbital theory, and we're too early in organic chemistry to start looking at molecular orbital theory. It's too hard to look at. So what we're going to do is we're going to use resonance structure as our tool for explaining things and realize that it's not like this structure over here exists and this one exists and they're bopping back and forth as it used to be taught way long time ago. It's that there's a real structure and Lewis dot structures can't help us with what is the real structure. So what we do is we look at the resonance structures and say the real structure is somewhere in between those two. It's kind of like an average of the two. When we write resonance structures, we use a double-headed arrow. This is the only time we use the double-headed arrow. With equilibrium, we use two arrows, one pointing to the right and one pointing to the left. With resonance, we use a double-headed arrow. So try to keep that straight. When we go to write Lewis dot structures, we have this curved arrow approach for showing how the electrons move. An arrow represents the movement of two electrons. So if I have an electron moving from one bond away, that means the electrons have moved out of that bond to wherever that arrow is pointing. So if your arrow is moving the electrons away from an atom so that it has one less bond, that means the charge on it is going to have to become more positive. If there is an arrow coming toward an atom, that means electrons are coming to it, and so the charge is going to have to become more negative. So keep this in mind. As we do these and practice them, it'll become more natural, and you'll start seeing the electrons move. And thinking about the charge and how it changes will become pretty natural. When the bond leaves, when the arrow moves the electrons away, that means the bond has to leave because a bond is electrons. If you have an arrow coming into a sigma bond, that means another bond's coming in on top of it, so that a pi bond's going to be forming there. So bond leaving, if it's a double bond and you have electrons leaving away, that means a sigma bond's left. Arrow coming into a bond, that means a pi bond is forming. And so this will help you understand how the resonance structures are related to each other. And they're related to each other by the electrons shifting through the pi system. Okay, let's go ahead and look at an example of how we use these electrons and the arrows. If you look at this arrow, you can see the electrons are saying they're coming out of that bond and now they're going to reside on this oxygen. If I look on the other side of this double arrow, you see those electrons are over here now, and the electrons in that bond are gone. Now, what we can say is you can either take this negative or you can take the electrons from the non-bonding pair. It doesn't matter. Now we're saying, though, electrons are moving into this bond. That means they're leaving this oxygen and they're going into this bond. If they leave that oxygen, that means the negative charge leaves and goes into the bond. And if you look over here at this oxygen, you can see there's one less non-bonding pair. So the electrons here are jumping onto the oxygen as a non-bonding pair. As a result, negative charge develops there because electrons are moving onto the oxygen. Here, electrons are moving off the oxygen into the bond. So the non-bonding pair is gone, the bond is there, and the charge, actually, the oxygen becomes less negative, more positive, and so you don't see the negative charge there anymore. Hopefully this made sense to you, and we'll be going over more of this in the future. Here's an example of the bonds moving around and no charge developing. Let's look and see how this happens. The electrons here are actually moving to between these two carbons, so they form a new bond there. The electrons here are moving to this bond, the electrons here are moving to this bond, and you see those double bonds have essentially moved. If you look at this carbon, though, what does it do? It loses electrons and it gains electrons, so no net change in its charge overall. This one loses and gains, gains, loses, loses, gains, gains, loses, loses, gains. So every atom here in this, every carbon atom here in this structure both loses a pi bond and gains a pi bond, so there's no net charge overall. Here's another example. Here's the negative charge when the non-bonding pair jumping between these two atoms and forming a pi bond. Here the pi bond jumps out and jumps onto the oxygen to make another non-bonding pair and a negative charge. And here you see that over here. 3 non-bonding pairs plus a negative charge. Here the negative charge is gone because now those electrons are in this bond. If we move backwards this way, the negative charge jumps into that bond and the electrons here jump onto that carbon. What does that do? That puts a bond in here and puts the charge on that carbon, and you see that over here on this structure. Okay, so what I want you to do right now is go ahead and draw the other resonance structure this would have and draw the arrows that are used to show the formation of that resonance structure. Don't forget to draw your double-headed arrow between the two. Pause the lecture and then restart after you've finished this. Okay, here is this, the same structure as above. And what we have is these electrons are going to move between here, these two carbons. When these electrons move between these two carbons, this carbon actually can take another bond because it only had 3 areas of electrons. It can take a 4th. These electrons can be lost here because this carbon can accept a positive charge. And so the arrow is showing this bond jumping between those two carbons. It neutralizes the charge on this carbon and causes a charge to develop on this. Now, the arrow for it to go back and form the original resonance structure is these electrons jump from between these two carbons to between these two carbons. Notice that for resonance to occur, the double bond has to be conjugated to the charge. Conjugated means in line with it, like this. If there was a CH2 between this carbon and this carbon, it would not be able to do this because the electrons have to be able to jump to the next door bond to form a pi bond. And it wouldn't be able to do that if there was a carbon here that had 4 areas of electron density. So look for conjugation in forming resonance structures. Okay, go ahead and try this problem now. You see, again, a double bond and a negative charge. They're conjugated. They're adjacent to each other. So you can have a resonance structure here. Go ahead and draw the other resonance structure and the arrows to form it. Pause it and then resume after you've written your answer. All right. What we see here is you cannot draw the electrons going from this bond toward this carbon. Why? Because that is saying electrons are going to be attracted to a carbon that has a negative charge. That does not occur. The only thing that makes sense here is for the electrons here on this carbon to move into this bond, and then these electrons jump up onto the carbon. That's what makes a symmetrical molecule. It's basically the mirror image of this one, but it's done by the electrons moving, the electrons in the non-bonding pair here moving into this bond as a pi bond with this sigma bond, and this pi bond jumping as a non-bonding pair onto this carbon. So why is resonance important? The reason that resonance is important is it gives stability to the cation, anion, or free radical. And the stability of those species is important in determining speeds of reactions and the direction in which a reaction will go. So if you understand resonance and stability from resonance, then understanding organic reactions is going to be a lot easier. Anytime you have a pi bond with a carbon adjacent that has either a positive charge, a negative charge, or a free radical, you are going to find that resonance exists. So in the future, if you're wanting to see if there's resonance, look to see if you have a pi bond conjugated to those charged species or a free radical. Some resonance structures really are identical to each other, like some of the all-carbon resonance structures that we saw in some previous slides. But here, these resonance structures are different from each other in that here an oxygen, let me show you here. Here the oxygen has a negative charge, and here the carbon has a negative charge. These two resonance structures have a lot of difference from each other. So what we have is when we have a difference in the resonance structure, what we find is they contribute to what is considered the real structure differently. So let's look at these two structures. If we look at this structure, we see there's a negative charge on the oxygen. And if we look at this structure, there's a negative charge on the carbon. Well, you yourself know that oxygen is more electronegative than carbon. So which of these structures do you think would be more stable? Well, this actually makes more sense, doesn't it? Because oxygen is better able to bear a negative charge than a carbon. So what we find is greater than 50% of the real structure is due to this structure, and less than 50% is due to this one. There's more charge that actually resides on this oxygen, less charge that resides on the carbon. So maybe 60% of the charge might be on this oxygen and 40% on the carbon, or even more like 75-25. I don't know what the exact percentages are, but the idea is that the two structures are not equivalent, and so this structure has greater importance than this one. That doesn't mean that this structure is not important, because what we find is when the molecule that these two resonance structures reacts, or the anion that these two structures represent reacts, what happens is, depending on the reagent that they react with, it might react with oxygen or it might react with the carbon. And we use the characteristics of these two and their contributions to the overall structure to explain why it occurs the way that it does. Now what I want you to do is go ahead and draw the arrows to show how this resonance structure moves back to this, just to give yourself some more practice. Well, first of all, you would see that a non-bonding pair, you can say the negative charge, jumps between the carbon and oxygen to form a pi bond. That carbon cannot have 5 bonds. Carbon can never have 5 bonds. So what happens is it has to lose a bond. What bond does it lose? This one right here. And those electrons jump onto this carbon. And that gives us this structure over here. And there's the arrow to show that. Okay, here's another example of 3 resonance structures. Which one is least important? You would say this one is. Why? Because here oxygen is holding the negative charge, and here oxygen is holding a negative charge. That doesn't mean that this isn't important in reactions. It just means where would we expect to find most of the negative charge? On this oxygen and on this oxygen. But this part of the structure is still very important, and we use this to explain why this particular species undergoes a lot of reactions. But we use these 2 structures to explain why the entire anion is relatively stable. So go ahead now and draw the arrows for this species becoming this species, and then this species becoming this species. Pause it and then restart after you've drawn in your arrows. Okay, for this structure, we would have to have the electrons jump in here. See, it would form this double bond, and then jump in here to form this double bond, and then to jump up here to form that negative charge. Notice, if the carbon gains a bond, it loses a bond. If a neutral carbon gains a bond, it loses a bond. Neutral carbon gains a bond, it loses a bond when it stays neutral. Notice, this has 4 bonds, that has 4 bonds. Well, this had 4 areas of electron density, this has 4 areas of electron density. This has 4 areas of electron density, this has 4 areas of electron density. Notice this went from negative to neutral. Why? Because it lost electrons going over here and jumping up there. All of this has to make sense in order for you to draw them correctly. So here's another structure for you to try. Go ahead and try to draw another resonance structure. Use the arrows to push the electrons around to figure out how that structure is formed. Pause and then restart after you have figured the answer. Okay, this is the other resonance structure. How would you draw your arrows? You would have to have the electrons going toward the positive charge and forming this bond here. So you would draw your arrow like that. For this structure to go back here, these electrons have to go in here toward a positive charge and form that bond between them.